For the entire age of the universe, the best clocks we have would lose only a single second. That's a level of precision that is almost impossible to comprehend. But what if I told you that scientists are now on the verge of building something 10 times better? A timekeeping device so accurate, it could change our understanding of the fundamental laws of physics and even help us find dark matter. This isn't science fiction. This is the story of the thorium nuclear clock. For the past few decades, our gold standard for timekeeping has been the atomic clock. These incredible devices work by harnessing the quantum world inside an atom. Specifically, they lock onto the incredibly consistent frequency of energy needed to make an electron jump from one energy level to another. The vibrations of these electrons are so stable that we've used them to define the international standard for what a second is. Today's most advanced optical atomic clocks, which use lasers to track these electron jumps, are the ones that are so precise they'd be off by less than a second over 13.8 billion years. So you might be asking, why on earth would we need anything better? Well, even these paragons of precision have a weakness. The electrons they rely on are in the outer shell of the atom. Think of it like a fluffy, delicate cloud. This outer cloud is relatively exposed and can be jostled by stray electric and magnetic fields in the environment. These tiny disturbances can subtly shift the electron's energy levels, introducing tiny inaccuracies, or noise, into the clock's tick-tock. For most applications, this is perfectly fine. But if you want to push the boundaries of science, to test the very foundations of reality, you need something even more stable. To do that, scientists decided to look deeper, past the fluffy electron cloud and into the very heart of the atom, the nucleus. This is the leap from an atomic clock to a nuclear clock. The nucleus is an incredible place. It's about 100,000 times smaller than the atom itself, and it's unbelievably dense. This compact, tightly bound nature makes it incredibly well shielded from the outside world. Those stray electromagnetic fields that can bother the electrons barely have any effect on the nucleus. So a clock based on a transition within the nucleus, rather than a transition of an electron, promises to be significantly more stable and reliable. By some estimates, up to 10 times more accurate than the best atomic clocks we have today. This idea has been a holy grail for physicists for decades, but it came with one gigantic problem. Exciting an atomic nucleus is not easy. The energies holding it together are immense. Nuclear transitions typically require energy in the range of millions of electron volts. To trigger that, you'd need something like a gamma-ray laser, a piece of technology that we simply do not have. The dream of a nuclear clock seemed impossible, stalled by a massive energy barrier. But it turns out, nature left us a loophole, a 1 in a billion exception, and its name is Thorium-229. Back in 1976, physicists theorized that a very specific isotope of thorium, Thorium-229, had a special property. It possesses what's called an isomeric state. This is a long-lived, excited state of the nucleus. But what made this one unique was its incredibly low energy. Instead of millions of electron volts, the energy needed to kick the Thorium-229 nucleus into this excited state was thought to be just a few electron volts. This is a mind-bogglingly small amount of energy for a nuclear transition. It's so low that it falls within the range of vacuum ultraviolet lasers, meaning, for the first time, we had a nuclear transition that we could actually poke with existing laser technology. The reason for this ultra-low energy is a beautiful, delicate accident of physics. It's the result of an almost perfect cancellation between the two most powerful forces in the universe, the strong nuclear force, which binds the nucleus together, and the electromagnetic force, which tries to push the protons apart. Inside the Thorium-229 nucleus, these two titans are locked in a struggle that just happens to result in an excited state with barely any extra energy. It's a cosmic coincidence that makes the nuclear clock possible. However, knowing this transition existed and actually using it were two different things. For nearly 50 years, scientists were on a frustrating quest to find the exact energy of this transition. It was like trying to find a tiny, invisible curb by dropping thousands of tennis balls from the top of a skyscraper and trying to measure the minuscule differences in their bounce. Experiments gave a wide range of values, making it impossible to tune a laser to the precise frequency needed. But then, after decades of searching, the breakthroughs started coming. In 2023, a team of scientists managed to narrow down the energy level with unprecedented precision. And then, in early 2024, came the moment physicists had been waiting for. Researchers successfully aimed a finely tuned laser at thorium nuclei and, for the first time, directly observed the light emitted as the nuclei decayed back to their ground state. They had finally hit the target. They had made the nucleus tick on command. This direct laser excitation was the crucial, missing piece of the puzzle, and it opened the floodgates for the development of a real, working nuclear clock. So, how do you actually build one? There are two main designs being explored. The first is called a trapped ion clock. In this method, scientists take a single thorium ion, an atom with one electron removed, and trap it in an electromagnetic field inside a vacuum chamber. Then, they use lasers to cool it down to temperatures just a fraction of a degree above absolute zero. This isolates the ion almost completely from the outside world, creating a pristine environment to probe its nuclear transition. It's incredibly precise, but its reliance on a single atom can limit its long-term stability. The second approach is the solid-state clock. Here, instead of a single trapped ion, scientists embed millions of thorium-229 nuclei into the crystal lattice of a transparent material, like calcium fluoride. This allows them to query a huge number of atoms at once, which can dramatically improve the clock's stability. The challenge here is that the crystal environment itself can slightly interfere with the nucleus, so researchers have to find ways to shield the thorium from these local interactions. More recently, a hybrid approach has emerged, using thin films of thorium compounds. This would require far less of the incredibly rare and expensive thorium-229 isotope, and because there's less material, it would be less radioactive, making the technology safer, more accessible, and even portable. Now we get to the really exciting part. What can you actually do with a clock this precise? This isn't just about building a better stopwatch. It's about building a new tool to explore the universe. One of the most profound questions in physics is whether the fundamental constants of nature are truly constant. Are the laws of physics the same today as they were a billion years ago? Some theories that go beyond our current standard model of particle physics suggest that values we take for granted, like the fine structure constant which governs the strength of electromagnetism, might be slowly changing over cosmic time. The energy of the thorium-229 transition is exquisitely sensitive to the interplay between the strong and electromagnetic forces. Therefore, a thorium clock is an incredibly sensitive probe for any changes in those constants. By building a thorium nuclear clock and an advanced atomic clock and letting them run side by side for years, scientists could detect even the slightest drift. If the two clocks fall out of sync in a specific way, it could be the first concrete evidence that the laws of physics are not immutable. A discovery like that would be Nobel Prize-worthy, completely revolutionizing physics. Then there's the hunt for dark matter. We know this invisible substance makes up about 27% of the universe, but we have no idea what it is. One theory suggests that dark matter isn't a particle at all, but a sort of ultralight field that permeates all of space. As the Earth moves through this field, it could cause tiny, wave-like oscillations in the fundamental constants. An individual clock might not see this, but a network of synchronized nuclear clocks spread across the globe could. As a dark matter wave washes over the planet, each clock would experience a tiny blip in its timing. By correlating the signals from all the clocks, we could potentially detect these waves, giving us our first ever direct handle on the nature of dark matter. Beyond these mind-bending scientific quests, nuclear clocks would have a huge impact on our technology. The Global Positioning System, or GPS, that your phone uses every day relies on a constellation of atomic clocks in orbit. The timing signals from these clocks are what allow your phone to calculate your position. With the superior precision of nuclear clocks, GPS accuracy could be improved from the meter level down to the millimeter level. Imagine autonomous cars that can navigate with perfect precision, or systems that can monitor the ground swelling over a volcano, or shifting along a fault line with such accuracy that they could provide warnings of eruptions or earthquakes. Our entire digital world, from high-speed internet to secure financial transactions, depends on the precise synchronization of data networks. The next generation of communication technology will demand even greater timing precision, a need that nuclear clocks are perfectly poised to meet. Of course, the road ahead still has its challenges. Building the specific kind of ultraviolet laser needed, one that is both powerful and has an extremely narrow frequency, is a major engineering hurdle. The key ingredient, Thorium-229, is also incredibly scarce and expensive to produce. And a lot more research is needed to fully understand and mitigate the subtle ways the environment can affect the nucleus, especially in solid-state designs. But the scientific community is incredibly optimistic. The progress in just the last couple of years has been astounding. The tantalizing prospect of a device that can probe the fundamental nature of reality is a powerful motivator. The journey of the thorium nuclear clock, from a wild theoretical idea in the 1970s to a tangible reality today, is a testament to human ingenuity and our relentless quest to measure the world with ever greater clarity. We stand on the cusp of a new era, where the very fabric of time can be measured with a fidelity once thought impossible. The age of nuclear chronometry has truly begun.